is the second video on problem solving and focuses on classical mathematics. So the previous video introduced a technique for problem solving. That is, how do we tackle problems which are not a simple reproduction of problems covered in notes and lectures. And we've noted that some of these might even be open-ended, that is, they do not have a single correct answer. So the proposal we gave was to use 3 simple steps. First, ask yourself, what is the topic? And write down whatever you know about this topic. Now that could be things like formula, laws, assumptions, conventions, and so on. So write these down briefly to start with. Secondly, look at what information have I been given. And does this link to the information I already know, and can I use the two together to create some new information? Now, once I've got the new information, I may find that I can use that in combination with step 1 to generate even more new information. For example, new information might say, oh, there's another topic involved here. What do I know about that topic? And so on. Now, the most important thing from a student's perspective is that problem solving is the skill that is most prized by future employers. So it's important that you develop this skill. So some background. Remember, we're talking about mathematics here. So step 1 expects students to list what they know. It is implicit, therefore, that students have a comprehensive awareness and competence with core mathematical tools. You will not be able to do problem solving in mathematical areas if you don't know the basic maths. Students need to be able to collect a list of what these tools might be and always have those tools to hand. Now, here's something you can always do. If you've got a data sheet of key mathematical formula and laws, these are widely available, then you can always look it up if you're thinking, oh, this is about topic X. What do I remember? What was that law? I'll just look it up on the sheet, and then you can see it. You never know in advance which formula might be required, so you need to be able to put your hands on them quickly when you need them. Now here's some typical topics for maths, things that you might want to include in your data sheet. So things like trigonometry, vectors, matrices, calculus, indices, logs, hyperbolic functions, complex numbers, Taylor series, and so on. You can see there's quite a long list, but as a competent engineer, these are the sorts of math skills that come up all over the place, so you need to have those math skills to hand. So what I'm going to do now is illustrate some problems which are not just simple exercises, but which are more problem-solving exercises in mathematics, and we'll work through how we use the technique to solve these. First one is relatively straightforward. So we're given a solid prism of length 3 meters, has a cross-section which is a regular 12-sided shape, with each side having a length of 1 centimeter. Now, this prism must weigh a maximum of 30 kilograms, be a good conductor, but not be too soft. What material is it likely to be made of? And you can see that this question is pretty vague. It doesn't say you must get it exactly right. It says, well, what do you think? So how do we go about this? We're going to use our problem-solving technique. First, ask ourselves questions like, what is the topic? And what should I know about this topic? Next, only after I've done that, do I start thinking, well, what information have I been given? And can I use this information with the information with what I already know to create new information? And then 3, clearly, is the iteration step. Right, let's ask some basic questions about data. We've been told it's a solid prism of length 3 meters, a cross-section, which is a regular 12-sided shape, with each side of length 1 centimeter, weighs at most 30 kilograms. What material is it likely to be made of? So here's the question, what is the topic and what do I know? Well, clearly, this topic involves shapes, volumes, areas, okay? And in order to do those, it involves trigonometry. So I need to have to hand key formula and data that relate to those topics. It also talks about mass, 30 kilograms, so I need to know about topics like density and mass of materials and properties of common materials. So those are some things that I need to be writing down in the corner before I start this problem. what information have I been given? And can I use this with what I know to create new information? So I've been given dimensions, length 3 meters, each side 1 centimeters, 12-sided shape. So I could do a sketch. I'm not much of an artist, but essentially you've got a shape that goes round like this, and that angle in there has to be 30 degrees because you've got 12 sides, and we've been told that that side is 1 centimeter. So with that information, I can actually work out the area, or the cross-sectional area, of this prism. Now, I'm not going to go through this in slowly because I'm sure you can work it out yourself, but clearly the cross-sectional area is 12 times the area of that triangle. And the area of that triangle is given by 0.1 times 0.01, because it's 1 centimeter, times 0.005 times tan of 75, all divided by 2. So that's half the base, which is 1 centimeter, times the height, and the height is 0.005 times tan 75 over 2. So that's the area of that triangle. If I multiply that by 12, I'm going to get the cross-sectional area. And the volume of the prism is going to be 3 times the area, and if you plug all these numbers in, what you'll get is 0.0034 meters cubed. Okay? So I've used the information I've been given, and I've combined it with knowledge that I've already got, which is how do I find the area of a triangle, how do I find the area of this prism, and how do I find the volume. So that's just reiterating the point. Now, I know I've just gone and written over that bit, so if I just delete that so you can see what it says, the next bit is to find the mass. Can I find the mass? Well, once I've got the volume, another formula that I know is that mass equals volume times density. Okay? Now, I haven't been given the density, but I have been told that the mass must be at most 30 kilograms. So I can put rho is less than or equal to 30 over 0.0034. And that tells me that rho is less than or equal to, now I'm going to be approximate here, 8,900 kilograms per meter cubed. So you see what I'm doing here, okay? I'm bringing in common knowledge, things that I know. What's the formula for mass? Down here. Okay, I'm sorry, what happened to that red line there? What's the formula for volume? What's the formula for cross-sectional area? And I'm combining that with things that I know to work out something different. And what I've got now is the density must be less than 8,900. Okay. So next, so I've done those, I need to look up some common information. So what are the densities of common materials? Okay, the density of copper, 8,800, density of steel, 7,800, density of lead, 11,000, density of aluminium, 2,700. And I've worked out that I want the density to be less than 8,900 kilograms per meter cubed. So I can see immediately it could be copper, could be steel or iron, but it's not going to be lead. Now, what about aluminium? Well, if you look back at the question, you'll have noticed it said it didn't want the material to be soft. And aluminium is quite soft. So I'm going to reject that one. And what do we get left with? Well, it's going to be something like copper or steel or iron. Okay, so the likely material is steel, copper or iron because lead is too heavy and aluminium is too soft. Now the next question, this one's mathematically a bit more complex, but it really does illustrate the skill of problem solving. So we're talking about a flying fox. So if you know what a flying fox is, you can see this man here basically hangs on a wire and then shoots down the wire and drops off at the bottom. And what we want them to do here is to land in a pool of water at the bottom. Now, our problem is, at what point the rider should be dropped so that they land in the pool of water rather than landing somewhere else. And the pool of water is 50 meters along from the start point. Now here's the problem. The rider's speeds may vary by as much as 10 miles per hour due to having different weights and drags. And one of the other things we've not put down here is how wide do we want this pool to be? We don't want the pool to be too big because it costs lots of money. So do we want the width to be 5 meters, 6 meters, 7 meters, or so on? Okay. Now we're going to assume, and this is given, this is information provided, that the flying fox wire, that's this wire here, has a curve which can be represented as h equals 20e to the minus 0.04x, and the pool is at a height of 0. So that's information that you're given. So here's the question now. You've got a problem here. The problem is, where should the rider be dropped? Okay? And you've got lots of information. How are you going to tackle this particular problem? I know we're told at the bottom the pool might only be 5 meters long. Is this safe? So what's the topic and what do I know? Well, we know the topic involves simple functions. We're given that the wire is an exponential. But we also know that once the rider lets go of the ride, they're in free fall. And the equations for free fall are parabola. So there's things that I know. I should know the equation for an exponential, the equation for a parabola, and properties of those curves. We know the problem is going to involve some physics, as the rider is accelerating due to gravity. So we need to have to hand what are the formula related to acceleration due to gravity. We need to know how velocity is linked to position. So clearly this rider is going to have a different velocity at different points, and we need to know what those velocities are, because without those velocities we can't actually look at the physics either. We need to know the trajectory for the person in free fall. We have to work out where they land, okay? And what we know is they may have an initial horizontal and vertical velocity, and based upon that we need to know where they land. So what does that tell us about what is the topic and what do I know? So these questions here are telling you what do you need, and that's helping you identify the topics, the information that you need to pull out of your data sheets and elsewhere. Well, you can see that it's going to involve tangents, because the rider can be assumed to be following a tangential direction on this wire. So if I know the tangential directions, I can work out things like the initial horizontal and vertical velocities once they let go. Therefore, I need the equation for a tangent. So there's lots of things there that we've written down, lots of topics that are involved in this problem, and the first thing I would do is say, okay, what are the equations I know around these topics? Because if I haven't got those equations written down, then I won't know how to use the information I'm provided with. So what information am I given? I'm given the landing point should be 50 meters from the start point, and the rider therefore has to be dropped at some point prior to 50 meters. Hopefully that's obvious. We're given that the wire follows an exponential, and thus we can determine the vertical drop for any given distance x. So that's the information we're given, nothing else. Okay? Now here's the equation for the drop. You were given that h equals 20e to the minus 0.02x. So that's the curve for the wire, but the drop basically says is what's the distance that you've gone down from when you started. Well, if you started at 20 when x equals 0 and you're now at this height, then the drop is the difference between the two. So that's information essentially that you've been given. Now on release, the rider's velocity is assumed to be tangential to the wire at that point, and thereafter they're going to follow a free fall trajectory. And the actual velocity could be 10 miles an hour slower than that determined from ideal physics. So that's information you were given as well. So what I've got to do now is link the knowledge I've got to the information I've been given. And please note, I don't really direct myself at solving the problem at the start. The first thing I do is say, how can I use the information I've been given? What new information can I generate? And as I generate new information, it will be obvious how this can be used to solve the problem I really need. So what we're going to do, use some ideal physics. So if I write that down there, use ideal physics for now. And so we're going to assume no energy is lost during the descent, and there the velocity at the release point is based solely on how far you've dropped from when you started. And therefore you get a standard physics equation. You're probably familiar with this. V squared equals 2as. So the velocity squared is twice the acceleration times the distance travelled. That's the sort of formula you come up with. And so you've got v squared, that's the velocity of the person, equals 2 g acceleration due to gravity, and then here's the drop, 20 minus 20 e to the minus 0.02x. So v squared equals 400 times 1 minus e to the minus 0.02x. And we emphasize this is based upon ideal physics, so assuming no energy loss during the drop. Now once released, this rider is going to follow a tangential direction initially, and that's what this curve down at this graph down here is indicating, that when they're released, they're going to be following a tangential direction. So we want to ask ourselves, what is this tangential direction? Well, if I know x, I can work out the tangent dh dx by differentiating h. And there it is. And what I can tell you is this is going to give me an angle theta. Okay, so at a particular value of x, I will have a particular angle of theta. Now clearly, I've got a minus here, because the person is coming down, but you'll notice that minus and that minus can cancel, so you get tan theta equals 20 times 0.02 e to the minus 0.02x. And therefore, I can now work out the vertical and horizontal speeds. So the vertical speed here will be vy, the horizontal speed will be vx, and the tangential speed will be v. So I can write down vx equals v cos theta, and vy equals v sin theta. So I now know how fast the rider is going down and how fast they are going across at the point they are dropped. Now, once we've released, we're going to assume, again this is simple physics, the horizontal velocity is constant, so it will stay at vx. But the vertical displacement is going to obey standard physics, dropping due to gravity. So what you're going to get is this equation here. Again, you'll recognize this is a standard physics equation based upon somebody who's accelerating with a constant acceleration. So you'll see we've got initial velocity vy times the time, plus 0.5 times acceleration due to gravity times t squared. T is the time they're dropping. Now, how far do they drop before they hit the water? Well, we know the height when they were dropped. It was 20 e to the minus 0.02x, so that's the total distance they're going to drop. And so if we solve this equation, that's going to tell us the time, okay, that it takes them to reach the bottom. So you see we've got height above water and released, vertical speed at release point, and we can use this in order to determine the time at which they hit the water. So if I solve this quadratic, then okay, this formula doesn't look very nice, but that doesn't matter. That's part of being an engineer, not getting phased by formula looking a bit messy. But there's a key point here. This quadratic has two solutions, but it's very easy to prove that one of those solutions has negative time. And we only want the solution which is in positive time. So I've got a unique solution now for the time. And I'm going to keep that formula because I'm going to need that in a minute. Let's go back to the original problem. We want to find where and when the rider lands. If we assume the drop time is known, then the final landing place is given from this formula here. The landing place as a position x is where they were dropped plus the horizontal velocity after they were dropped times the time after they were dropped before they hit the water. And so landing x, that's where they're going to hit the water. Okay? We already know t, vy, and vx. So we can just plug those in and find where we land. So here's the formula for t. Once you tell me the dropping value x, okay, I can plug it in to here. So I'm going to put all the formula down so you can see how we do this basically in a sequence. You give me x, and from x I find theta. Okay? You give me x, and from x I find v squared. Once you've given me v and theta, I can find vx and vy. Once I've got vy and x, I can go in here to find t. Once I've got t and vx and x, I can go here to find where the person lands. And you notice what I've done here. I've constructed formula using what I know and what I've been given, and then once I've constructed all this formula, I now can see how to solve the problem. Okay? It does, however, look quite messy. So what am I going to do next? Because I really don't want to be doing this by hand. Well, here's a warning. Don't expect a neat analytic solution to real problems. It just isn't going to happen. And also don't expect a unique solution, because that's not likely to happen. You'll probably get a family of solutions, and from those you have to express a preference and argue a preference. In this particular case, the simplest approach is probably to plot a graph of dropping position versus landing position, so where they're let go by the flying fox and where they land on the ground or the water. Now, because this is quite numerical, I'm going to suggest you use a computer rather than doing it on pen and paper. So that's what I've done here. You'll see I've started with a column x, and I said, right, you assume that the dropping position is x. From that, I can work out theta and v. Once I've got theta and v, I can work out vy and vx, and then I can work out t, and then finally I can work out the landing position. And plot all those numbers down, and then you'll see I've plotted dropping position x against the landing position. So for example, you'll see if you drop them after 30 meters, then where they land is somewhere around 47 meters. So it's very easy to create this graph. However, if you look back in the question, you'll see we said, wow, the actual speed at dropping could be 10 miles an hour slower than that expected from using ideal physics, because you'll get some variability due to the rider and other things. And so I've plotted a second line here, this red line, which is what you get if you assume that the velocity when you drop is 10 miles an hour slower, which is 4.44 meters per second. And you'll see you've got a different line. And so within this line, you've got the variability in what might happen with different riders. So for example, if you drop at 30 meters, one rider is going to land here at around 37, 38 meters, and the other rider is going to land here. So there's quite a variability in where they might land, because there's a variability in the speed they've got when you drop them, if you drop them at the same place. Okay? So here's a question. Is this ride going to be safe? All the riders are going to land in different places. So this is the sort of thing I can do. I want the dropping position, or rather the landing position, to be 50 meters. So let's mark that down. Here's the landing position. This is where I want them to land. And what does that tell me? Well, if you're on the blue curve, the dropping position is here, whereas if you're on the red curve, the dropping position is here. Now in practice, I'm going to have to drop people at the same place. So if I drop people at the same place, how am I going to make sure that they land in this pool of water? So for example, let's assume that I drop everybody here at about 37 meters. That's where I drop them. Then you'll see one of them lands here at something like 47. Another one lands here at somewhere like 55. I've got a variability in where they might land. So how am I going to make this safe? And you can see what we've said at the top here. The pool is going to have to be substantially larger than 10 meters to make sure that people land in this pool of water. If there's an 8-meter variance in where they land, and then I need some gaps at each end to make sure they don't hit the ends, I'm going to need the pool to be something of this type of length in order for this ride to be safe. So some conclusions. This video has given 2 examples of problem solving using mathematical skills, and the proposal is to ask the right questions and identify what knowledge is relevant. What topics might be involved, and what should I know about this topic? So that's step 1. What information have I been given, and can I use this in combination with what I know? And this might lead to an iteration between steps 1 and 2. Critically, it's shown that real problems might not have clean analytic or even unique solutions, and you may need